Okay, so in this video we're going to talk about inverse trig functions and specifically the calculus dealing with them. If it's been a while since you've looked at your inverse trig functions, I'd recommend going to my YouTube page. There's a category for trig videos, and the videos that you'd want to watch are titled Inverse Trig Functions, Part 1, Part 2, Part 3. So again, I would strongly encourage you to go to that and review that before starting the video if it's been a while since you've worked with inverse trig functions. Okay? And so we're going to start with the derivatives of inverse trig functions, and one of the things that you'll need to know or at least have access to will be the graphs of these inverse trig functions. So page 417 has all of these graphs. I would encourage you to pull that up as well while we go through this. So we'll go ahead and we'll start here with the derivative d dx of the inverse sine function. And that derivative is going to be 1 over the square root of 1 minus x squared. And for all of these, the chain rules would apply as usual. I'm just not going to write them out. We'll look at a few examples though. Okay, so I do want to go ahead and prove this. Very rarely will we just assume something is accurate in math. At least at this level, we'll prove what we can. And this one's not too bad. So I'm going to start by letting y equal the inverse sine of x, which means the sine of y equals x, noting our inverse properties. And then I'll go ahead and take this guy right here and d dx it. Remember, many of our proofs are going to utilize things that we've already learned. And so for us, we're taking something we don't know, and then we're utilizing an inverse property and then turning it into something we know, hopefully then to back substitute at the end. We've done this many times. Okay, so then on the left, the sine of y would be a cosine of y, and then the derivative of the inside would be a dy dx. And then on the right we have equals 1, and so dy dx would equal 1 over cosine of y. All right, so now remember, we kind of know what this is supposed to go to, right? We know it's going to turn into this. Our numerator looks good, but our denominator's got a fair amount of work. So we're going to use a trig identity. We're just going to use the basic fundamental identity from trig. The cosine squared plus sine squared equals 1. And of course, we're going to manipulate it to solve for cosine. So if I solve that Pythagorean fundamental identity, that fundamental identity was cosine squared plus sine squared equals 1. If I solve this for cosine, I'll subtract the sine squared, and then I'll square root both sides. I'd end up with a plus or minus the square root of 1 minus sine squared y. And we know from the start that sine of y is equal to x. So there sits our 1 minus x squared. So from here, the dy dx is going to be plus or minus 1 over the square root of 1 minus x squared. So we're almost there, right? That's almost what we want, but our derivative, notice, is going to be the positive one. Well, why is it the positive one? Why can't it be this negative here? Why does it have to be only the positive? And that's because of the graph. If you go back and look at the graph on page 417, you'll note that the slope of every single tangent line on that curve is going to be bigger than 0. Therefore, your derivative has to be positive with the way it's presented. Okay, so there's the derivative for inverse sine. Now, I'm going to use the same screen, maybe just to save space and a little time. Next to it, I'm going to write d dx of the inverse cosine of x. This derivative is not going to take a lot of convincing. It's going to be a negative 1 over the square root 1 minus x squared. The reason I say it's not going to take a lot of convincing is because, in theory, if I let this be a cosine instead of a sine, we would essentially do the whole thing the same way, but instead we'd have a 1 minus cosine squared here. So, in other words, we'd end up with the same thing here as well. Now, we also end up with a negative, which is kind of obvious if you look at the graph. The graph of that cosine, inverse cosine, graph B on page 417, you would see the slope of all of its tangent lines would be less than 0. And that's why we have to accept the negative as part of its derivative. Okay, so now we'll take a look at the derivative of the inverse tan function, and that's going to be 1 over 1 plus x squared. And so we'll go ahead and we'll prove this one as well. The proof is going to be very, very similar. We're going to let y equal the inverse tan of x. We'll say then that the tangent of y equals x, and at this time we'll ddx both sides. The left-hand side turns into a secant squared of y dy dx because of that chain rule equals 1. And then the dy dx would have to equal 1 over secant squared y. Now, this is where we make that substitution with one of our Pythagorean identities. We know that secant squared is actually directly equal to 1 plus tangent squared. And from the beginning, we know that x equals tangent of y, so I'm going to plug in my x, and I'll get my derivative without a whole lot of work on this one. One of the observations that you should make, though, is notice that this thing is always positive, and if you look at the graph for the inverse tan on page 417, you would once again find out that the slope of all those tangent lines are always bigger than 0. That's an increasing function on its entire domain of negative to positive infinity for this one. Now, I'll follow it up just like the last slide, where we have now a similar conversation about the inverse cotan, where you would see the derivative to be negative 1 over 1 plus x squared. Almost the same exact process. In fact, if you wanted to stop the video and rework it, you would find out that it is almost the exact same thing. In fact, this one being negative is supported by the fact that the m tan on this graph is going to be less than 0 on its entire domain. So again, a couple of nice comparisons, one next to each other, and then very similar to the previous couple as well. All right, and so finally, before we get into some examples, we've got the derivative of the inverse secant, and it's going to be 1 over the absolute value of x times root x squared minus 1. So let's go ahead and prove this one. If we let y equal the inverse secant of x, then we know that the secant of y would equal x. ddxing both sides is going to give us now a secant y tangent y dy dx equaling 1. And then that dy dx is going to equal 1 over secant y tangent y. So I went kind of fast through that because honestly we've done it, this is our third time now, pretty fast, so I don't think there's really any concern there. But I do want to slow down a little bit now when it comes to the substitutions. Okay, using our Pythagorean identity, we know that 1 plus tangent squared y equals secant squared y. Okay, that's one of those identities. And so if I solve this thing for tangent, my tangent of y would equal plus or minus the root secant squared y minus 1. That's what I'm going to replace this guy right here with tangent. And then we know that secant of y equals x. So there's going to need to be my x there. And then I'm replacing that with the plus or minus square root. Okay? So dy dx equals 1 over. There's that x. And then times plus or minus the square root of secant squared y minus 1. And we'll knock out this next part in one step. First of all, we know that secant of y has been defined as x. So I'm going to change that into x squared minus 1. Similarly, if you look at the graph for inverse secant on page 417, you'll notice that that's an increasing function on its entire domain, which means that the slope of the tangent line here has to be positive. So we're clearly going to take the plus right there, but that's also where the absolute value bars come on the x. We have to keep that derivative positive. So we're going to have the absolute x and then the positive root x squared minus 1. And so there's our proof now of the derivative for inverse secant. The d dx of the inverse cosecant, much like the other two, is very similar. Instead, it would be a negative 1 over the absolute value of x, root x squared minus 1, and it follows almost exactly the same way. And I would encourage you to look at the figure on page 417 one more time to confirm that your derivative needs to be negative, because the mtan on the entire domain has to be negative. Okay, so there's a rundown on your derivatives for the inverse trig functions. We'll go ahead and take a look at a couple examples. Okay, so the first one we're going to look at is the inverse secant, and we know that we're going to have a chain rule here because of that x to the fifth being inside the function. So for the y prime, we'll start with 1 over the absolute value of x to the fifth square root the x to the fifth squared minus 1, and then back times the derivative of the inside, which would be 5x to the fourth. Okay? So remember, that derivative template, if you will, that we started with was 1 over the absolute value of x, root x squared minus 1. In our case, the x is going to be equal to x to the fifth from right here. Okay? So by plugging all that stuff in, this would be considered an unsimplified derivative. I want to tidy this one up just a bit, though, to explain one thing. So I guess I'd have a 5 on top, wouldn't I? Let's put a 5 up there to start. So when it comes to this x to the fourth here and this absolute x to the fifth, we can divide some of those off. But remember, you're going to have 1 left here in the denominator, and because x to the first would be odd, we would still want the absolute value bars on that x. But they could be divided off traditionally as well. And so this would then be an x to the 10th minus 1. And there's your simplified derivative for the function. All right, so for this one now, if you look real close, you'll notice we're going to have to find the derivative implicitly in this case. We can't solve explicitly for y, so the implicit derivative will be found by starting to d dx both sides. So on the left side, we've got the derivative of inverse sine as 1 over the square root of 1 minus that inside squared. Okay? Back times the derivative now of the inside. This is the derivative of the inverse sine of this thing. Now we need the derivative of the inside. And this will need to be a product rule. Derivative of x with respect to x is 1 times the second, plus derivative of the second with respect to x would be a dy dx back times the first. Then on the right, pretty similar, because if you remember, the derivative for inverse sine and inverse cosine are the same, except that we have a negative for this inverse cosine. So it'll be a negative 1 over the square root of 1 minus whatever's inside, back times the derivative of the inside, which in this case would be a 1 minus dy dx. Okay? Now, we still would need to solve this for dy dx, and it looks pretty messy, but it's really not that bad. The first thing I would do is I would essentially multiply by the LCD to kill these fractions here. So this guy's going to be multiplied over here, this guy's going to be multiplied over here. So I'm going to get a square root of 1 minus x minus y squared times a y plus x dy dx equals a negative square root of 1 minus xy squared times 1 minus dy dx. Okay, so I multiplied this guy over here, and that negative is the same as that negative. And I'll tell you what, to kind of clean it up a little more, that negative, I'm afraid I'm going to lose it out there. I'm going to distribute it through here, and let's just call this dy dx minus 1. So how about we erase this right here, and how about we change this to a dy dx minus 1. That's just a smart way of avoiding losing that negative somewhere along the way. It's very, very easy to do, so we'll go nice and slow through that. Okay, and so from here, I'm actually not going to finish the rest out for you. I think you guys can probably handle it from here. All you would need to do is the same thing you would do every other time. You would distribute each of those. Then you would get everything with a dy dx on one side. You would factor it out. Everything without a dy dx is on this side. And then you would just divide off the part that you don't need. Okay, so just basic algebra. You've done it many, many times in a problem like this. Moving on from this, we'll transition now into the integrals of inverse trig functions.